Let's begin with a simple assumption. Take the entire hydraulic braking system from a four-door sedan and install it on a 40-ton tractor-trailer. On a technical diagram, everything still follows the correct principle. Press the pedal. Fluid transmits pressure. Brake pads. Clamp onto a disc or drum. Nothing is theoretically wrong. But the problem is not theory. It is mass. A passenger car weighs about 1.5 tons. A fully loaded truck can weigh 20 to 25 times that amount. At 60 kilometers h, the kinetic energy that the braking system must absorb does not merely increase slightly, it scales directly with mass. That means a single press of the brake pedal generates dozens of times more heat. At this point, the difference between hydraulic brakes and air brakes is no longer about convenience. It becomes a question of physical limits. Hydraulic brakes operate in a sealed system. When the driver presses the pedal, a piston in the master cylinder forces brake fluid through lines to the brake chambers at the wheels. Because brake fluid is nearly incompressible, force transfers almost instantly. The pedal feels firm. The response is precise. And the system is ideal for passenger cars in urban environments. However, brake fluid has an inherent weakness. It has a boiling point. Standard DOT. 3 fluid boils at around 205 degrees Celsius when dry, while DOT4 reaches roughly 230 degrees Celsius. These numbers may sound high, but during a long downhill descent, continuous friction between brake pads and drums can push temperatures to or beyond those levels. Once the fluid reaches its boiling threshold, vapor bubbles begin forming inside the lines. Gas can be compressed. Liquid cannot. That distinction is critical. When the driver presses the pedal, instead of transmitting force directly to the brake pads, part of that force is absorbed, compressing the vapor bubbles. The pedal becomes soft. Its travel increases. Braking force drops significantly. This phenomenon is known as brake fade. In a passenger car, it is dangerous. In a 40-ton steel vehicle descending a slope, it becomes an unacceptable risk. Now imagine a real scenario. A tractor hauling 30 tons of cargo, with a total combined weight of 45 tons, descends a mountain pass at 70 kilometers per hour. Kinetic energy is proportional to mass multiplied by the square of velocity. Double the speed, and energy quadruples. Multiply the mass by 25 compared to a passenger car, and the braking system must manage energy at a corresponding scale. Friction at the brake surfaces converts motion into heat. That heat accumulates in discs and drums, then transfers into the brake fluid through the pistons. In the closed loop of a hydraulic system, heat has limited pathways to dissipate. If the driver must ride the brakes continuously, temperature rises second by second. When brake fade sets in, the driver feels the pedal turning spongy, but the vehicle's mass does not respond to that sensation. Inertia continues, pushing the truck forward. At this moment, the system does not automatically transition into a safer state. It simply becomes less effective. Air brakes tell a different story. Air does not boil in the same way fluid does. When temperature increases, air expands, but it does not form disruptive vapor pockets because the system is already designed to operate with compressed gas. The design accepts the nature of the medium rather than working against it. Hydraulic brakes depend entirely on remaining sealed. A small crack in a line, an aging rubber seal, or a minor leak at a fitting can reduce pressure. As pressure drops, braking force weakens proportionally. The system does not automatically lock. It simply loses strength. Air brake systems take the opposite approach. Trucks carry multiple compressed air reservoirs, typically maintained at 8-10 bars. If the compressor fails, the stored air remains sufficient for dozens of brake applications. The driver has time to slow down and pull over safely. More importantly, when pressure falls below a safe threshold, powerful mechanical springs inside the brake chambers automatically expand and lock the wheels. The system does not wait for human input. It assumes that loss of pressure signals danger and shifts to a stopped state by default. If hydraulic brakes were applied to a heavy truck without such a mechanism, loss of pressure would simply mean loss of braking. There would be no backup spring-forcing engagement. No automatic safe position. Only a soft pedal and a massive vehicle still in motion. So the question, what would happen if trucks used hydraulic brakes, is not merely a technical thought experiment. It reveals how a principle that works well at small scale can become hazardous when magnified many times over. As mass increases, small margins shrink. Minor weaknesses turn into major risks. In a world of machines weighing tens of tons, design cannot focus solely on efficiency. It must be engineered to fail in the least harmful direction possible. If scenarios like this make familiar systems seem suddenly unfamiliar, next time we could imagine the same question applied to elevators or airplanes. In those fields, the concept of fail-safe design is pushed even further because when scale and consequence grow, safety must be built into failure itself.